Hey guys, it's Chili here. A little bit of a different kind of video for you guys today. Consider this a pilot for a new series. So what it's going to be is every time I have a coding challenge, I'm probably going to present two solutions. One will be the basic algorithm with standard C++, and another one will be the optimized algorithm that's probably going to have a bunch of parallelization bullshit, maybe some other optimizations in there as well. And what I'm going to do is in the solution video, I am going to present the basic algorithm, the derivation, the concept, the implementation in a shorthand form. And then for you guys, as a special bonus, I will present, I'm going to go into in-depth, I'm going to give an in-depth explanation of my ultimate solution. As you can see, the ultimate solution is a lot more bullshit in here than in the basic solution. So it's gonna be a bigger pain in the dick to do this, but I figure, you know what, as a bonus for you guys, if you're interested, then I will present this as an option for you guys in the Patreon dashboard. You can unlock it, which you obviously have done if you're watching this video right now, and you can watch it. So we'll see if you guys are interested, if I can actually see a lot of people unlocking and watching the video, then I will continue to make these videos when I do coding challenges. If not too many people are interested, then I'll just drop it and do the basic solution only. So that's the idea. Now let's take a look at my actual solution. So we're going to run it using the test harness. We'll use the same test suite that I used to evaluate all the submissions. And it's not a super big test suite. It's got the file tests that I gave you guys, maybe a couple of extra ones, bunch of randomly generated tests with different seeds, small amount of, I think these ones all have maybe like 8,000 or 2,000 entries, I can't remember. And then a couple of special generated ones, all ascending, all descending, different sizes, small size, large size, and then very large size solutions. And sum them all up, 11.72 milliseconds, which is pretty close to the same runtime I got, on the results that are on the dashboard. So that is how this performs for 80 million integers. It's about 7.25 milliseconds. This one's also 80 million integers, but there's a little different case. This is a special case, or you could say that this one's a special case, depending on your point of view, but we'll get into that in a second. To achieve this time, this was the fastest time. The next fastest was 18 milliseconds, and it actually used I think pretty much the same approach that I used. Maybe one difference, which I will get into. But, so yeah, this result was achieved using the same algorithm that I showed you guys in the basic solution video, but there are three optimizations that I applied. Two are parallelization, and one is a kind of a special case. So parallelization, you can do it usually two ways. You can vectorize, and you can multi-thread. And I'm not going to go over what it means to vectorize, what it means to multi-thread. That's something that you're going to have to, it's on you to know that. This isn't a basic video, it's an advanced video, it's not a tutorial. So, vectorizing and parallelizing. We can do both on this problem. Let me show you how to parallelize it first. It's not that hard. So you guys know the basic solution. You're going to run over. That's a really bad rectangle. Let's use our functions of our software here. There we go, much better. So you've got a range of values, container, and you run the big O(n) algorithm on that, and that gets you the maximum difference. Now, what if we wanted to parallelize this? What would you do? Well, the first thing you'd think of is, well, what I'm going to do is I'm going to split it up into, let's say, two parts to do, two threads. And I'm going to run my algorithm on this part, and I'm going to run my algorithm on this part. So that'll give me the maximum difference within this part of the container and the maximum difference between in this part. So I'll get, max 0, max 1. and then I just take the max of that to find my ultimate maximum. And that's a good start, but it's not going to work. Why? Well, imagine that my minimum value, say minimum is 3, and my maximum value is 400. My maximum and my minimum are in different parts of the container. It's not going to compute this difference because it's only working within this set and within this set individually. So because we can't consider differences that cross boundaries, that cross sections, this simple approach won't work. So what we do instead is when we run over the container, we don't only produce the max diff. So we do the max diff, the same algorithm that we've been doing in every section, but we also yield the min value and the max value for every section. And so now we have, max diff 0, min value, max value 0. And here we have max diff 1, min value 1, max value 1. And then what we do is after we have calculated these 3 values for every section, we run our algorithm on these values, and we basically say, first of all, what is the what is the maximum inside of any particular section? And we take the maximum of all of those, and so that is the individual max. We'll call this Imax. I don't know. Doesn't matter. But then we also run the algorithm. We check the differences in between sections. So we would take the min val here, and we would take the difference between the max value here, and we would compare that result to the max value that we have from inside of our sections, and we take the maximum between all of those. So we do our algorithm on individual sections, and then we reduce those all to a single maximum. And that's how you do it with multi-threading. And of course, if you increase the number of sections, you just have to do more comparisons, but it's the same idea. So that is the first optimization that you can consider, multi-threading. And if you've got 4 cores, this is pretty much an embarrassingly parallel problem. So the cores don't have to communicate with each other. You're pretty much going to get a 4 times speed up as long as you have the memory bandwidth required to do that much data access. You're going to get 4 times as fast. So if the naive solution is around 250 milliseconds, your solution is going to be around 60 milliseconds if you can leverage this kind of multi-threading. But as you can see, mine is 11 milliseconds, quite a bit faster. So the other thing that you can do is you can vectorize. So on a single SSE register here, you can break it down. You can use it as a register that contains a vector of 8 16-bit integers. Signed or unsigned or whatever, it doesn't matter. Now there is a function called min pause, and what it'll do is it'll basically go through this entire register, all these 8 values, and it will find the minimum value, and the result is going to contain nothing in the top 6 values. Here it is going to contain the minimum value, and here it is going to contain the index of that minimum value in the original vector. So you can use this single instruction to do a parallel search over 8 elements at a time, find the minimum one. And the beauty of this is if you can find the minimum, you can also find the maximum. Because what you do is, well, let's say I want to find the maximum value. If I take all of my values and I subtract them from the largest possible integer, I'm basically going to invert the relationship. So now the one that was the largest will become the smallest because it will be subtracting the most from this value. And the one that was the smallest will become the largest, and therefore min pause will then function as max pause. So you can do these kinds of transformations in order to to get the instructions that you want, because the SSE, it has a limited amount of instructions, and they don't have all the variations that you might want. There might only be one variation, and to get the other variation, you've got to do a bit of transformation. We'll get into that a little bit when I go over the code, which I guess is going to be right now. So the idea, let's just go over it quickly here. The idea is you've got this big container of values, and you're going to load them, in our case, because we're working with 16-bit values, we're going to load them 8 at a time and process them in chunks of 8 using these special instructions, these vector instructions. As much as possible, we're going to try to vectorize this. And then we can combine that with the multi-threading, separating the container into very big chunks, into basically 4 big chunks, because we have 4 cores. And then we can get some amazing speed up, because think about it. 4 times speed up from multi-threading, because you got 4 cores. Theoretically, you're going to get about 8 to maybe 6 times speed up from SSE, because we're working in chunks of 8. So we're looking at, you know, maybe up to 24 times speed up when you use those techniques both together, because they multiply. Pretty good shit. So let's take a look at the code. So the basic idea here, let's first look at the multi-threading part, because it's simpler. I create a struct sub-solution. It has the things that I told you about, the maximum value, the minimum value, and the maximum difference. And this will store those values, report those values for each section that we run. Each section will correspond to a thread, which will correspond to a core on our CPU. So down here, I've just got a simple function here, allocate units, that will take the number of work units, basically the number of elements in our container, and it will distribute that to an amount of work units for each thread. So it just basically divides the number up, but since sometimes it won't divide equally, it distributes them so that some threads will have 1 extra work unit, some threads will have 1 less. But it's very simpler. Very simple, just distributing the work across a number of threads. So, solve function is going to, well, we've got a function here, solve sub, that solves the sub problem, that returns a sub solution. And we'll go over its implementation later. But what solve is going to do is, first off, if the size of our work group, our problem, is fairly small, less than 200,000 elements, we're not going to bother multi-threading it. It's not worth it. We just call solve sub on the entire thing and return the max difference part of that, and that's the solution done. But if we have a larger work group, then we're going to engage our multi-threading. And what we do there is we create, well, first I do a little const expr, set my number of threads to 4 because I'm working on my machine, which has 4 cores. And I create an array of threads, size t and threads. So that's the workloads. So it's an array of size t, and there's 4 elements, and that's just going to store the amount of numbers to process for each thread. And then I call allocate units on that to set it up. So I mean, if the number of workloads or the number of numbers is divisible by 4, it's just going to put the same number in each element in this array. But if it's not divisible by 4, it's going to, you know, have a little bit of a difference by one, just by 1. So we set the number of work units, basically the number of elements that each thread is going to process. Then here is another array, and this one stores futures. So we're using std_future here to spawn threads, because std_future uses a thread pool, so it's going to be more efficient. And it's also a lot sexier because you can get a return value from your thread like it's a normal function. You can spawn a thread, you can launch it, and you can get a return value from it like you're calling a normal function. It's a little different, but it's sexier. It's much sexier to use std_future than to manage threads manually. It's a very pleb way of coding to manage your threads manually. Unless you have a good reason, std_future is always going to be the sexier, the smarter, and often the faster way to do it. So we create an array of futures, And then for every one of our elements in our future array, what we do is, what do we do here? So the offset is going to be the offset in the array, the input array. So we launch solve sub. We give it a reference to the input. We give it offset where it has to start in the input. And we give it the number of workloads that it's going to do. And yeah, that's it. And so we create our futures. That's going to launch 4 threads that will start working immediately. Then what we do is we create another array that's going to hold the solutions. So this holds a future for the solution. We have array the solution. And then for a little sexy standard library bullshit, I call std transform. Over all the futures, output is going to be into this solution array. And for each future, to do the transformation, we just call get. So this will block now on all of our threads. And when the first thread completes, it will put that result into sub-solution. Then it'll try to get from the second one. And when it completes, and so generally it's just going to block while all threads are running. It's going to block on the first one. And then they're all going to complete around the same time. And it's going to get all the values and put them in here when they're complete. Then we're going to have this array of sub-solutions. So now we run our algorithm, or a modified version of our algorithm, over the array of sub-solutions. So we get the minimum, which is just going to be the min value from the first section. And we get the maximum difference, which is going to be the maximum difference from the first section. And then for all the other sections, we check to see if the minimum is less than the maximum value in that section, in the current section under examination. And if so, we update the maximum difference to be that the current maximum difference, the maximum between the current max and the difference between the maximum value in the current section and the minimum value encountered so far over all sections that you've examined so far. And then we update the maximum difference, also taking into consideration the maximum difference within the current section. And then we update the overall minimum, taking into account the minimum value in the current section. And we run that over all our sections. So this is also an n algorithm, but n is the number of threads. So obviously it's very tiny. It doesn't impact the performance of the final thing. But there you go. There's how you reduce all of the sub-solutions to a final single max difference that you return. So this is the multi-threading part of the algorithm. Now we get into the actual solve sub, which is the vectorization part of the algorithm. All right, so as you have seen, solve sub takes constant reference to input, which is a vector of unsigned shorts, and it's going to take the index for the start of its section and the length of its section that it's to work on within that input vector. So what we're doing here, first off, because we're doing, SSE, I'm going to set up some, I usually do this, I set up some useful vectors that I need to use down here. I just make some constants. So one is this bias value. I'll get into that in a second. But it's setting, just copying into all the 16-bit slots, all 8 slots, copying this value here. And ones is just copying, all binary ones into all the slots. So just setting the entire 128 bits all set. Max shorts biased. What is this? This is the maximum value of a short that has been biased. It doesn't make any sense right now, but I'll explain in a second. Broadcast low short. This value is kind of important. This is a mask for an instruction called shuffle. What is it called? I don't know what the intrinsic is. Shuffle something, epi8 or something. The instruction is called pshuffb. It's an incredibly versatile instruction that allows you to dynamically reshuffle the contents of an SSE vector, an SSE register, based on some mask. So here we're setting this mask, and what this mask is going to do, so let's say we've got a register here. It holds 8 16-bit values, and we want to broadcast 16-bit values into every 16-bit slot in a destination register. So what we do is pshuffb shuffles by bytes. So we're going to actually be shuffling these 2 bytes into, you know, here like this. AB, 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 AB. And that is what this value here does. That is the mask that is needed to perform that broadcast operation. And this, where is it? Let me just find it so I can shuffle. Okay, shuffle epi8. It's extended packed integer 8 or something. I forget what the E stands for, but it's packed integer 8. So yeah, and for the details of pshuffb for that instruction, you can see, and just in general, if you're interested in learning the basics of this SSE vectorization stuff, I have a series on that. It's called SSE Hand Relief. Very nice. And yeah, just Google that and look, it'll get you started on the basics of how memory loading works and how integer SSE works. You'll learn all the stuff, including shuffle bullshit. So yeah, if you find yourself lost but you're interested, definitely watch those videos. There's like 4 of them. They're pretty long. There's tons of information in there. But anyways, so we got our shuffle mask. We got something that I'll explain later. So our 3 registers that we're going to be working with are not registers, but values. I don't know what you want to call them. Vectors. We'll call them vectors because that's what they are. All right, so we've got min so far biased. And this is going to contain basically the minimum value that we've encountered so far. We'll see in a second what this bias bullshit is. Max diff so far complemented. So this gives us the maximum difference that we've found so far. And max so far complemented gives us the maximum value that we have encountered so far. Now we're going to loop over our entire range, but we're going to do it using pointers. So we're going to cast this stuff to constant pointer to SSE value of vector. And now we're going to be looping through pointers. Now here is the third, this is the third optimization right here. And what this one does is if the maximum difference so far is I think 65,500 and something 36 or 35. If the maximum difference so far is the maximum that you can possibly get, you just return right away. So this is actually huge, but we'll talk about it in a second. It's huge, but we'll just put it out of your mind for a second. Pretend this doesn't exist. So what are we going to do? Well, first thing we're going to do is we're going to load a chunk of 8 shorts from memory. So we call load. Fairly simple. Now we're going to bias them for signed compare. Because what we want to do is we want to compare the values that we've loaded against the minimum that we have encountered so far. Because if we find a new minimum, we have to update that. But here's the thing. There is no comparison function for unsigned 16-bit integers in the SSE instruction set. So we cannot do an unsigned compare, but our values are unsigned. So what do? Well, we can transform our unsigned values into a signed range that still keeps the relationship between them. So in the unsigned domain, our values range from 0 to 64K, basically. Whereas in the signed range, they're going to range from negative 32K to positive 32K. So what we do is we actually add 32K to our unsigned value. We give them all a bias. So what is 32K in hexadecimal? That's 08000. I ran out of my tablet thing is not aligned properly. I cannot write past this point. Anyways, it's OX00, it's OX8000. Now, in binary, that means the top bit is set. So this isn't going to be a negative number. This is actually the largest negative number that you can get is OX8000 in signed 16-bit numbers. So when we add this value to the smallest signed number, you get the smallest unsigned number, because this number here is this is the smallest negative signed number. So this is negative 32K. So this one here, OXFFFF, is negative 1. This is negative 32K. So by adding this number to the smallest unsigned integer, you get the smallest signed integer. So what happens if we add this to the largest unsigned integer? Well, the largest unsigned integer is OXFFFF. If we add OX8000 to that, you get OX7FFF, which is the largest signed integer. So by adding this, we maintain that the largest number is still going to be the largest number in the signed domain, and that's the smallest. The smallest is still going to be the smallest, and the largest is still going to be the largest. So add this number, and you have a beautiful transformation. And then when you want to go in the other direction, you can subtract that number. So this is the meaning of the bias. That's the magic number that you got to add and subtract in order to be able to use this comparison instruction, or this comparison intrinsic, which translates to an instruction, maps directly to a specific SSE instruction. So that's one complicated part here. Where is that? Yeah. Compare less than epi16. So we do that, that gives us a mask, and then we test that mask. And if none of them are smaller, we don't have an update to our smallest possible value. Then what we're going to do is, well, here's the thing. So we want to use this instruction. Where is it? Minpos EPU16 to get the position of the maximum value. So how do we do that? Well, like I said before, we just subtract our values from OXFFFF, and that means that the maximum becomes the minimum and the minimum becomes the maximum. So we flip them, we get the complement by subtracting our loaded chunk from ones, which is just all Fs. That gives us the chunk, the complement of the chunk, and then we find the maximum value and the index of that maximum from that complemented chunk. So this will give us the maximum of the original chunk, which is the minimum in the complemented chunk. You see, this is very complicated. It's a little complicated, but I hope you can follow me so far. So now we have the complement of the maximum value. So what we want to do is now update the maximum that we've encountered so far by taking the maximum between the maximum in the current chunk and the maximum that we've seen so far. But since it's a complement, the maximum is actually the minimum, so we take the minimum. There we go. Now we have updated the maximum so far. So this vector right here, it contains in the very lowest 16-bit section, it contains the maximum within the chunk complemented. So the maximum value, the complement of the maximum value. And now we want to subtract the minimum so far from that to get the maximum difference within this chunk. But the problem is this one is complemented. The minimum so far is not complemented, so we have to complement it first. So we do the subtraction here to get the complement. And then what this actually does is it gets the complement and it unbiases it, because the minimum so far is biased, but that doesn't match with this one. This one's complemented, not biased. So we got to complement it and unbias it, and this does it in one step. So now we have them in the same domain. They're both in the complemented unbiased domain. So now we can subtract one from the other. We get the difference, and then we update the maximum difference by doing the minimum, because they're in the complemented domain. And there you go. You've updated your maximum difference. And this is the basic step. So you run and you're looping and you're doing this. But sometimes you're going to run into a new low value. So this is going to go to false, and you're going to get a new low value. And what we do then is, if you find inside of the vector that one of the values is a new low, it's very tricky. There's a lot of different cases. So instead of processing that situation in a vector way, what I do is I bring it back into the scalar domain and I process them with a scalar loop. And then I transform back into the vector domain, and then I continue. Because this case of finding a new lowest value, it's actually fairly rare in most data sets. And I've processed it even in data sets, large data sets that are pathological, and it doesn't really have a huge performance impact. So that's what we do. This thing here, that's just convert single integer 128 into single integer 32 bits. So it takes the lowest 32 bit in the vector and it converts that into a integer. And then we add 800. That is to unbias the minimum. That gives us the min so far. So we convert. We basically, in terms of CPU, this gives us an instruction that is going to move data from the vector part of the CPU into the scalar part. And then we do this adding to bring it into the normal domain. And for this one, we got to uncomplement. So again, we bring it into a different part of the CPU and we uncomplement it. And here we're also uncomplementing the max so far. So max difference. We run the algorithm as usual over the 8 shorts in the current chunk. And then here we bring it back into the vector domain. So this does the vector domain and the biasing, I guess. Yeah, this is the biasing. Subtract. I thought biasing was adding, but it could be subtracting. Actually, it could be either one could work. I don't remember anymore. It doesn't really matter. In either case, bring it back into the bias domain, into the vector part of the CPU, and then we got to broadcast it to all the slots, because the min so far is used where? Right here. We compare every value in the chunk against min so far. So we've got to put the min so far, we've got to broadcast it to every slot in the vector. So here we're doing the broadcast. That's the thing I was talking about before. And then more complementing and moving things into the vector domain. This one we don't have to broadcast because we're only really interested in keeping it in the lowest slot. That's the entire algorithm. You test to see if you've got a new minimum. If not, you update the maximum using vector operations. If you do have a new minimum, which is generally going to be a rare case, then you do a scalar scan over the 8 shorts, and you calculate you do the algorithm scalarly just over that 8 short span, and then you have to transform into the scalar domain and then back into the vector domain. And there you go. And then when you are done, one last time, you're going to transform into the scalar domain. You're going to fill your sub-solution structure, and you're going to return that. And that's it. Now, so that is the vectorization part. So we've covered the multi-threading, we've covered the vectorization. The last optimization that I sort of quickly glossed over is this, the short circuit, I call it. Because when you think about it, you've got a span of integers here, and they range from 0 to 64K, what is the probability that you're going to encounter a maximum value after you have already encountered a 0? What's the probability? I don't really know what it is, but I'm going to guess that once you've gone over, you know, 1 million values or 10 million values, you probably have a pretty super fucking huge chance of having this encounter already, because you've only got 64,000 unique values to go through. So the thing is, once you have reached this condition, you already know the answer. It cannot be anything other than 64K. So you might as well, once you've reached that point, exit immediately. And what this does is, for the basic general situation, the most common, probably the most common situation that you would consider is your values in here are just going to be equally distributed probability over all of the possible values. And in that situation, you're going to have an expectation, a statistical expectation of reaching 64K by some number of entries. That's not going to change depending on how many. So you can add, after that, you can add 1 million, you can add 1 billion, you can add a quadrillion more entries to the end of this. Statistically, you're expecting to reach this at about the same point in the container every time. Of course, you know, it's statistics. So sometimes you're going to reach it here, sometimes you're going to reach it here, sometimes you're going to reach it here. Very, very rarely you're going to reach it over here, but mostly, statistically, on average, you're going to reach it about here. And so what this does is, by adding this short circuit, you basically convert this algorithm from big O of n to a big O of constant time when n is, you know, much, much, much greater than 64K. It is going to basically be constant time, because it's going to always run the same time no matter how big it is, as long as it is above a certain size. Statistically, amortized. Of course, you know, on a special case, you might get a 0 here, and you might only get the 64K value up in the, you know, quadrillionth element. And in that case, you're not going to get this. But in general, for an equal probability, for every value, for every distinct value, you're going to expect, you know, pretty fast return. So that's why I added this short circuit in here. We are comparing the max difference so far complemented to 0. And remember, the complement of 0 is FFFF, which is the largest possible value. So we're checking to see if the max difference so far, if we've already maxed it out, can't be any larger. And if so, we just return that. And that is the reason why you get this performance here. Let me just wait for the... it doesn't take long for it to run the tests, but it takes very long to generate the test data set. So here, we've got Choky Big Boy, Choky Boy Big, and Shorty Boy Big. So Shorty Boy Big is just random, full range of values, 80 million integers, and it completes in 88 microseconds. And the reason why is because it reaches the maximum very quickly and it returns short. Now, Choky Boy Big is, I generated a test data set to screw people over who use this optimization. So in this case, it generates random numbers, but it doesn't generate, I think it it chokes the range down to between 5 and the maximum -5. So it reduces the range so that the algorithm cannot be sure that it has ever reached the maximum possible, and so it has to run to the end. And that was just to make it, you know, to make a fair comparison between different kinds of algorithms. So people who have implemented this short circuit will get a bonus, but they won't get a free pass. This is basically how it works. And there you go. There are the 3 optimizations that led to the 11 millisecond runtime. Couple things to mention here. Number 1, you can probably see now why I made the data set multiple of 8. The reason why I did that was to make my life easier because, you know, SSE loads in chunks of 8 16-bit integers. But that doesn't mean that, oh, Chili, you cheated because you set the problem specifically so you could use this solution. It's not it at all. If it was not a multiple of 8, I would just have to add another scalar loop at the end here. It would not affect the runtime. It would just make things a little more of a pain in the dick for me to write, which means it would take a little longer, which means you guys would get less content. So I adjusted the problem so that I could write this ultimate solution a little bit easier and therefore get you guys content a little quicker. But that's that. That's number one. Number two is, obviously, this is hella complex and tons of bullshit. So probably you're not going to be clear on all the points here. But if you're unclear on something, by all means, hit me up on the Discord or on the forum, and, you know, I'll get back to you. I'll try to answer your questions. Try to keep your questions as specific as possible. If your question is, I don't understand, then no. That just makes me angry. You've just made me angry. If the question is, Chili, how does SSE work? Then I'm like, yeah, that's not really a question. That's a whole course. But what I will say is that if you have no idea about SSE and you're interested, again, like I said at the beginning, check out my videos, SSE Hand Relief, and that'll get you started on the path to understanding the algorithms like this. And if you already have the background, if you understand a bit about SSE, but you're just unclear on a particular point in this algorithm, that's when you come to me, you ask me your specific question. I will be happy to give you a specific answer. But I think that's about going to do it for this video. You know, let me know if you liked it, that sort of thing. And that'll be part of how I gauge whether or not to make more like this. I'm fine either way. You know, this is a lot of work, but it is also, you know, it's fun to share it with you guys, and it's fun to reward people who have been supporting the channel and the work. So that's fine. But if people aren't interested, then I don't have to make this video, and that makes my life easier. It's less stuff to do. I can focus on other kinds of content. So either way, let me know. And yeah. I will see you soon with some more SSE bullshit, probably. Yeah, one little PS here I forgot to mention during original recording. And that is that if I actually reduce the number of threads from 4 to 2, it doesn't actually speed up the code that much. And the reason why is because basically I'm already at 2 threads. I'm pretty much maxing out my memory bandwidth. I'm processing the data so fast that you can't load the values any faster from memory. So any kind of optimization, throwing extra cores at it, or if you could somehow remove instructions, it still wouldn't help because at this point the code is bandwidth limited. Just one thing to point out there. So if I could, like if I could upgrade my RAM, if I could get some, you know, DDR4, maybe 3-channel or 4-channel, if those kind of form factors even exist, then yeah, I could probably get benefit out of all 4 cores. But as it stands, there is, I believe, only maybe like a 7% increase when I double the cores from 2 to 4. I get about double speed going from 1 core to 2 cores, but that's where you max out. That is where you hit the limits of the memory bandwidth of my system. I don't have any amazing memory in my DDR3 1600 dual channel, so it's not amazingly fast. And I did the math and I figured out, yeah, I am basically scraping up against that upper limit of the memory bandwidth. Alright, one final PPS here. Chili done fucked up just a little bit. So, after I had released the results on the Patreon dashboard, people were able to download my ultimate solution, and someone ran it with their own custom test data, and my solution failed the test, which is, you know, a little embarrassing. to say the least. So I got down to the bottom of it, and it was a dumb little error. It has nothing to do with the SSE or with the multi-threading thing here. It has to do with the function that allocates the units. So I don't know, perhaps you were able to catch this while you were watching the video. But it turns out that here, what I wasn't doing was I wasn't ensuring that each thread gets a data set, a work unit set that is a multiple of 8. It needs a work unit set that's a multiple of 8 because the chunks that it works in are a multiple of 8. That's how SSE works, right? 128 bits. So I did not do that, and that's why it would fail with that data set because it wasn't a multiple of 32, right? 8 times 4 threads, 32. It was some other multiple, and therefore my threads were getting data that was not a multiple of 8. So how I did that was I did a little const express here. I set the chunk size to 8. I set the number of chunks equal to the number of units divided by the chunk size. Number of groups, which is the number of threads, is going to be, you know, the size of the container that I pass in, the range. And then the group size, which is the base number of chunks for each thread, will be set by dividing. And then the overflow, which is the number of threads that will get an extra chunk because it doesn't divide evenly, is set here. And then in here we get the number of groups, the number of chunks, I should say, for each group, the base chunk size. We check to see if the group in question is going to get an overflow chunk, one extra one, using this expression here. And then we multiply by chunk size to get the final units, number of units for that group, the number of elements that thread will have to process. And if we do it this way, all the threads will be getting a multiple of 8, as long as the input number of units is also a multiple of 8. So that's great. That fixes the problem. And you run this, obviously it's not going to impact the performance of the algorithm. Just to be sure, I ran the algorithm over again. Actually got a slightly faster time than my original run, but I decided to leave it the way it is. So there you have it. A little bit of fuck up. So if I were submitting with everyone on the leaderboard competing, and if I had included that test in the test suite, I would have gotten 0 algos. So there you have it. But yeah, so there's the fix up. And one final thing that I think I forgot to mention so far is that I'm thinking of offering a little service for patrons who are doing the challenges. If your code fails the challenge and you're not satisfied and you want to know, then I'll offer there'll be a button you can request a manual review, and it'll cost a few chili bucks, and then I will review it and I will get the data, get to the bottom of it, give you the test results that is causing your code to fail. And if I do a manual review and I find out there's something wrong with my test or my system and your code is fine for some reason, then obviously you get all those chili bucks back and you'll be restored to your former glory. But it's just a little thing. I don't want to make it just anyone can request a review, because I don't want to be spending all my time reviewing stuff. But yeah, I think I might make that an option. Who knows? Let me know what you think. Anyways, that's that.